Welcome everyone at part 7 or session 7. In this session, we'll talk about the similarity measures and losses. We will see how actually similarity measures are the main functionality of neural networks, how neurons are acting as a similarity functions, and also we'll see how we can use some similarity measures or merely distribution similarity measures as a losses or as a cost functions. So we start with vectors or point similarity measures, which means measuring similarity between two vectors or actually between 2 points within our feature space. So for example, let's assume we have here two feature space. We have x1 here and x2. We have some data points that represent size, color, whatever features we have. This is our training or our experience data set. As you can see, this data set is unlabeled, which means we don't know to which class each point belongs. That's why we have uniform color. They all have the same color. But if we look at them, like just looking at them, we can see that this group, they have some kind of similarity because we have here dense, basically, distribution. So we can see that these points are close to each other. They are far from this group. So that kind of hint that they are similar and they are different from this group. But this is by just looking at the data set. So how we can do that automatically is by applying some mathematical similarity measures. So as I said, just by looking at them, we can see, okay, this group is similar, and this is maybe one cluster. This, for example, the clustering or unsupervised learning does that. Apply some mathematical similarity measures on the data set and try to group them without having labels or human labels. So that's why it's called unsupervised learning. So of course, the first similarity measure is the Euclidean distance, which is very known and very famous distance measure between 2 points in a vector space. And it's actually the Euclidean distance is basically the length of the direct line between 2 points. So for example, we have this point P0 and P2. The length of this link here, which is D1, this is our Euclidean distance. Now, the Euclidean distance, of course, is the square root of basically the sum of the differences. So basically, this is how the formula, if we have, this is basically the dimensions here with the first dimension and the second dimension. If we have more dimensions, we will also sum the difference. That's basically the square difference between them. And this is basically, if we look at the similarity measures with respect to Euclidean distance, we have D1 here, which is the distance between point 0 and point 2. And here, for example, the distance between point 0 and point 1. Of course, D1 is smaller than D2. That's why B2 is more similar to B0 than P1. For example, just as a simple, very simple way to do the similarity or to do the clustering here, we put kind of threshold. If the distance is smaller than this threshold, then all this would be group A. If it's bigger than this threshold, then it would be group B. The other similarity or distance measure, actually the Manhattan distance, is also known. It's also like the L1 norm, and it's actually L2 norm. And here it's actually the sum of the absolute difference between the 2 points, or also called the measured distance along axis at the right angles. For example, it is the sum of the length of this, for example, line plus this line, which is basically this is the L1 norm, as I said, or the Manhattan distance. And this also for the point 0 and point 1. So it's not a straight line, it's like projection of the two axes, and then we're summing that projection. It also can be used to measure the similarity between 2 points, and also we can see that, for example, D2 is bigger than D1. That's why this point is more similar to this one than P1 here. And this also we can use it to do the clustering or to basically conclude that this point, they are similar and more similar than these points here. Now, Let's assume we build a neural network based on Euclidean distance. So, as I said in the early lectures, each neuron represents specific feature. Each neuron actually represents a specific cluster. And for example, when we look at this data set, if we are applying some automatic cluster or automatic learning, we would actually have a neuron that represents this group and another neuron that represents the other group here. So the Euclidean distance itself is not used in neural network, but just here to understand how it works. So later we'll see the dot product which is used in neural networks, but here just to understand. So the neuron here represents a point. This point basically, if we are talking about k-means clustering or density-based clustering, this point represents the center of mass. Center of mass, basically, it's kind of the center of these points here, like we see there. For example, you take all the x-axes of the or x1 values, and you take the average along x and the average along y, and you end up with this center here. And this is the second center here. So now if I have a new point, let's say if I apply a new point there, or here, let's say, then we estimate the Euclidean distance from the first reference point, which is a green point here, which is represented by this neuron, and the second reference point is a red point here, and then the closer to, so for example, I talked earlier about the softmax. Here, let's assume that we have a negative softmax. So the softmax, as I said, it's basically normalize the values, which are called the logits here usually. Let's say D1 and D2, and D1 is smaller, as we said, than D2 because it's closer to the first reference point. So taking now this point here with the coordinates x1, 0, x2, 0s, and this is our input to the neural network. We calculate the Euclidean distance with respect to these two. The weights here, you can consider them as the coordinates of the reference point. For example, this is the first reference point with the coordinates W11, W12, which are these two. And this is basically the coordinate of the second connection or the second basically neuron here. So D1 is bigger than D2. Now, if I apply softmax, it basically would be the exponential of D1 divided by the exponential of D1 plus D2 here, and then the exponential of D2 divided by the exponential of D1 plus D2 there. This is how we normalize the logits. Now, if we only apply softmax, actually the value of D2 would be higher than the value of D1 because D2 is bigger than D2. So here I'm just putting 1 minus just to, because here we are not looking for the higher value or the highest value, we are looking for the smallest values. And here, for example, we are looking for D1. And if D1 is smaller than D2, then this neuron, the one that should be selected. And this neuron means, so what does that mean? For example, when I get now this input here, I'm applying these models, and this neuron would fire because, or would actually say that this point belongs to this class. And the other neuron cannot fire because it's far from its basically center of mass. This is how neural network works in general, but without Euclidean distance, we'll see later, it is actually with dot product. But each neuron actually represent cluster. It's called also sometimes kernels. And this is basically, the kernel is kind of mathematical function that covers a group or cluster of data sets. And this point, of course, now it comes to learning, as we'll see with the dot product, is basically the learning is to find this optimum point that split clusters or split groups from each other. And this is what is a feature extraction. What the feature that we extracted here is this point, because this point represents this group, and this point is another feature that represents another point there. So by doing that, maybe if now for all the input space, we can then do that kind of clustering, that all the point that from just here, basically, not mathematically, but just, for example, if we think about it, it would be, for example, this group is a group A and this group B, and this is our data. Basically, that represent our neural network here. Now, what is used in neural network is the dot product, which is related to cosine similarity. Cosine similarity is also very used in machine learning in general, and is, as I said, a part of the dot product. And the cosine similarity looks at the vector of points. For example, here we have 4 points in the vector space with 2 features, x1 and x2. These 2 points, they have the enclosed angle here, which is alpha 0, 1. That is the angle between 0 and 1. The cosine similarity look at the cosine of this alpha. The smaller the angle is, the higher the cosine value is, because, for example, the cosine of 0 is 1, and the cosine of 1 is basically 0. So basically, the smaller the angle here, the higher the cosine value. And this is basically the cosine similarity. So if the angle between 2 vectors is smaller than the angle between, for example, here between 0 and 1 is way smaller than between 0 and 2, that's why it is more similar to 1 than to 2. And this is how what is used in your network mainly, because if we look at the cosine similarity, and if we look at the dot product here, which is dot product between 0 and 1, this is basically dot product, which is usually equal to the cosine, the angle between these 2 vectors multiplied by the length or the magnitude of vector 1 multiplied by magnitude of vector 2. So if we look here at that, and our dot product, actually this one, is equal to cosine A multiplied by the magnitude. So we don't only consider the angle, we also consider the magnitude of these 2 vectors. Now, the neural network model that we have seen, which had the activation function, but before the activation function, we actually have dot product between the weights vector and the x vector, which is the input vector, or the layer before output, for example, which is here alpha when it comes to multi-layers. So here we have, for example, first the dot product, which is acting as similarity between the input x and the weight vectors here, omega 0. This is a similarity between input x and the weight vector w1. And the weights, as I said, they are representing connections here as well. This is how the neurons in your network are acting as similarity measures or similarity function. So looking again at this example, we have these points here, and we have this point there. Now, during the backpropagation, during the learning, we would learn omega 0 and omega 1 that basically they are in the same feature space. They are points in this feature space, but points that can split these 2 classes from each other. This point would be a vectors, as I said, as well. So this omega 0 is also a vector. Omega 1 here is a vector. And now, whenever we get a new point, for example, it will apply the dot product. For example, x here with omega 0, and here x1, x with, for example, or let's say this point with this one, we will take the dot product, and we take dot product with this one and this one. And then would be the higher dot product, mean the more, for example, closer or similar to this point, and we would do the clustering as we have seen the Euclidean distance. So if we look at a more advanced example of this, and we will see that later in convolution and neural network, basically, and machine vision based neural network, what we will see that, for example, in the first layers, which are the first, let's say, the first hidden layer, neurons learn some basic features of the image. If you are familiar with image processing and machine vision, usually the first step to do in order to do some intelligent decisions is to look for edges, to do what is called edge detection of the images, because they are the most important features. If we are looking, for example, the shape of objects, then first we need to extract their edges, then do pre-processing after that and post-processing, and maybe do another analysis to detect the shape of these objects. So when they apply neural network training on images, as I said, neural network is end-to-end learning, which means we don't extract features. We just put input images and we put targets like detect faces here, or detect cars, or detect elephants, or detect chairs, whatever. What we will see there is basically that the first neurons always learn to detect edges automatically. Now, they are different edges because they have different orientation there. They have, for example, they could have different scaling. But what is happening there is basically this neuron here would try to find a similar edge within the input image. What I mean by similar edge, we see here that we have black white edge. That means we have low intensity and then high intensity edge. For example, this is an image here, or this slide. Here we have white, then black, which means we have high intensity, then dark or basically low intensity. And this we have edge there. For example, for this case, this neuron would fire because this neuron would say, along all this edge, I have seen something similar to this feature. Now we will see later the convolution actually. What the convolution does is basically take a template, or here a feature that is learned, and this feature is basically one neuron, as I said. Then do the convolution, and the convolution basically is moving that pixel, or sorry, that template along the whole image. So convolution basically is scanning this template along the image, and then creating kind of output image. The output image basically is the output of this neuron here. This neuron would fire when it finds basically some features that are similar to the neuron. For example, as I said, when it reached here, it would find features that's similar to this edge. So in the output image, we would see basically some kind here of highlight at this position because it finds an edge similar to that, and dark everywhere. And because it finds similar features within the input image similar to this edge here. For example, this edge here, this neuron would fire because it finds another feature there that actually belongs to this neuron there. You would have, for example, some edges like this one, which basically would fire when it sees this one here, and this one would fire when it sees this edge here. So again, neurons are similarity functions. They are learned automatically. They learn automatically the weights, but they are in general similarity functions. So now comes the convolution that I just actually mentioned. Convolution can be considered as similarity measure between now template and a signal or image. So a template usually is a vector. As we have seen, for example, these two weights are templates. So this is basically two-dimensional vector. It could be 3-dimensional, it could be 4-dimensional. In images, we could have basically a metric 6x6, but it's also a vector actually. You can actually flatten to a vector. And what, for example, here we have a few examples here. We have basically a signal, which is the blue one. This could be the image that we want to process, or the input signal, or like a voice signal. And we have the template, which is here the red, basically template or the red, for example, neuron here. During the convolution, as I said, we do kind of scanning. For example, we move that template along the signal dimension. We do dot product at each position. Then we store the output of that dot product at that position, at the center of that position. For example, if we are here now, we do dot product between all these values and the values of blue one, which actually are zeros. Then we store the output value at the center there. And this is the output of the neuron, actually, or the template, or the convolution there. So you can see now when we start to find some similarity, the value here started to increase until here we have the highest similarity between these two templates, because here it's actually total match between the red and the blue, and then we see the highest similarity measure And then, of course, when you move it also, you see it now the similarity will be decreased and so on. Now, here is another example, and they are not exactly the same because this is the signal now. And our template, sorry. So we can see the similarity starts, and here actually the highest possible similarity, then it starts to decrease again. So this is how the convolution works. We will see it later. The main objective of convolution network and the convolution process is we don't take the image, the whole image as a one feature space, because if we have an image with, let's say, 1000 by 1000 pixels, so 1000 rows, 1000 columns, that means we have 1 million feature. And if we apply that on feed-forward network, that means each neuron here would be connected to 1 million neuron in the input layer. So that you can imagine that the number of parameters will actually explode. The idea of convolution actually is that we don't consider the whole image as an input feature. We are just considering small patches. For example, as I said here, we take here 3 by 3 templates, which means a neuron with 3 by 3 connection, which means a neuron with 9 connections. And this basically 3 by 3, every step would process only 3 by 3 part of the input image. Okay, so at each step we are not processing the whole image, we are processing small batches of the images. And then of course at the end we are concatenating the result in one complete image. And this is the main advantage of convolutions. The main advantage of convolution in the network is just to reduce also dimensionality, is to reduce the needed computational power. And of course, it's also more general because it looks for local feature, it looks for important feature than looking at the image as a whole, because the image as a whole could have a lot of redundancy, background details that we don't want. For example, if we're detecting faces, we don't care about the background. We only care about the face features. And what we see here actually, that in the second layer, the neurons learn more abstract or more actually here advanced features, because what is happening now after the first layer, we get now detected features which are the edges here. Then the layer after that, we start to take other features like eyes, because these eyes are kind of combination now of simple features which are the edges. Then we have nose, eyes, other parts of the face. Then another layer, which is the next layer, we would detect higher order or more complicated features like complete faces now. The same issue with cars. We start with simple edges, then part of the car like tires or for example the lights and so on, and then we complete part of the car. Elephant, chairs, the same. So that we basically will see later what in the convolution in your network. When we do have, let's say, deep neural network with multi-layers, then the first layers are simple features. Then the deeper we go, the more complicated and the higher abstract layers or features we get. So this is, for example, just a very high abstract feature, which is the face of this player, which is messy. And when we do that convolution, so when we convolve this feature along the input image, we would see something like this. We would see highlights, very high similarity value here in this position, of course. Everywhere else, it's dark to gray. Sometimes there could be some similarities between some features and some part of the face, but the highest basically value it is here, and this is basically where we detect the similarity. Now, up to now, we talked about the vector and vector similarities and also point similarities, for example, and we have seen the Euclidean distance, we have seen the dot product, and we have seen the convolution, which is dot product but scanned over the input space. Now we talk about, in this part, we'll talk about distribution or probability distribution similarity measures. That is mainly used now for loss functions in the neural network. But before going there, let's talk about some basics, which here talk about the entropy or channel entropy. which is the estimation of uncertainty of machines or random variables outcomes. So let's consider, for example, two machines, and these two machines generate a sequence of random symbols. So let's say we have A, B, C, D, and machine one generate kind of a random sequence like this, for example, AA, BC, AD, then AA, and so on. So generating sequence of symbols from this set, which is A, B, C, D. We have 4 symbols. We have another machine also doing the same. The difference between machine A and machine B is basically the probability distribution of, let's say, generating one symbol. For example, machine A has uniform probability distribution, which means it has 25% chance to generate A, and so this at each step of the sequence. So, for example, at the very beginning, I have 25% to generate A. In the second step, I also have 25% to generate A. Same for B, same for C, same for D. So it's basically here uniform. Now in machine 2, we have different probability distribution. For example, we have 50% always chance to generate A, 25% D, then 0. Or basically 12%, 12.5% for C and B. Now, just from looking at these distributions, if you want to talk about uncertainty or talk about randomness, or let's say if I ask you to guess now, so let's say machine 1 is generating now a symbol, and I ask you to guess what the symbol is. Then you tell me it's hard to guess because they are uniform. It's 25% for each. It's really kind of random. So if I guess A, it's high likely it would be B. But if I ask you about machine B, for example, or machine 2, sorry, you tell me most likely it would be A because A, 50% of the time, A would be present. And if it is not A, you tell me then it should be D because D is the second part of D. If it's not D, it should be either B or C. Now, one thing to know here, or to observe, that machine 1 has a higher uncertainty, which means machine 1 has a higher entropy. In this case, machine 2 is with lower uncertainty, which means machine 2 has a lower entropy. So entropy also could be, let's say, considered as the average number of questions to predict or to guess what is the outcome of this machine. So I just give you an example. If I want to guess now what is the symbol that's coming from machine 1, then I would ask, so we will need to start with the questions that I have when it comes to entropy, binary questions, which means the answer is yes or no. And here, in order to basically build this binary question tree for machine 1, the first thing to do is to split our choices to 50%. So it's a binary question. That means we need to split our options to 50%. So because here it is 25%, then 25%, then we need to split it, for example, AB or CD, or you can also do AD or BC. But let's say the first question to ask, is it AB? So is it AB as the output? Because AB here has a 50% chance of the data set or of the distribution. You would say yes. Then is it A? Because now is it A or B? Then A has here now 50% chance. Is it yes? Then A. No, it's B. For example, if it is not here, then it would be C or D. Is it C? Then yes. Is it, for example, D? Or is it not yes? Then it's D. Now here we have basically, on average, we have 2 questions to ask here in order to get to the decision. And this is basically the entropy. The entropy of system is 2 because the number of questions that we ask, or the average number of questions that we ask, is 2. And so, as I said, the higher the entropy is, the more uncertainty we have. And also, it's called the less information we get from this. So it's basically the less information you get from this, for example, machine. Now, machine 2, the number of questions is less because, as I said, the first question you would ask here, because A has already 50% chance, is it A? No, then the rest, because A has a 50% here. Then is it B, C, or D? No, would say is it D? Then is it, because D is the second now highest? Then no. If yes, then D. If no, then it's B, C. Then here yes, for example, or no. So if we go here now for machine, the first machine, and we want to calculate the number of question, or the average number of question, which is now the first estimator, the statistical estimator of the number of questions, we would start with, for example, the probability of the symbol A here, multiplied by the number of questions that I need to ask in order to reach A. So 2 questions to reach A, and the probability of A basically is 0.25. We have seen that. Adding to that 0.5, same for B, same for C, same for D. All they need 2 questions. So the number of questions I said in average to predict the outcome of machine 1 is equal to 2. Now when it comes to machine here 2, we actually have different, because for question A, or for example for symbol A, we have only 1 question to get to A with 0.5 probability, plus here 0.1, for example, 12%, 12.5% multiplied by 3 to reach to B. So we have, for example, first question, second question, third question, then we can get to B. So the same for here C, and for D we have 2 questions. So in average we have 1.75 questions to predict the outcome of this machine. So the average number of questions represent the level of information, or surprise level, or actually uncertainty level. The less the number of questions is, the lower the surprise and basically the information level. Entropy is the average number of questions, denoted usually by HP, and has unit bits, because as I said, we have our questions are binary, so it's like 1, 0 bits. So for example, 5 bits, that means we have 5 questions to ask. The higher the entropy, the higher the uncertainty we have. So the mathematical model, actually, we have here, we have seen that it is the estimation of basically the number of questions. So we need to multiply the probability with the event itself, which is the questions that we need to ask, which can be estimated by the log with base 2, but also you can see later it's not very important, base 2 or more. But for example, to really answer the number of questions when it comes to binary tree or the bits here, we need to use a base 2 multiplied by the 1 over the probability. So if we do that here, basically we would end with the this formula, which can be basically ending up with, for example, because 1 over the probability, or the log 1 over the probability, is equal to the negative log of that probability. So this is basically the known formula for entropy. Now this is the entropy. Something else to know to get to the similarity is the KL divergence. Now the KL divergence measures the difference between 2 different distributions, which means similarity. We have seen that when we measure the difference between 2 points, which means, for example, the distance difference between 2 points, that basically was used for similarity. Here also you can measure the difference between 2, or here actually the divergence between 2 distributions. And of course, the lower the divergence, the more similar 2 distributions are. It is used in deep learning as a cost function, mainly in autoencoders. We will see that later. KL divergence calculated as follows. The KL divergence, for example, between, how diverged Q, distribution Q is from distribution P, is equal to the sum, or actually the estimation again, of here basically the rates between P and Q, which means the probability of P divided by the probability of Q, which again, taking the negative here signal, it's actually the sum of the probability of X with the log here of Q divided by P. So here we're taking kind of the rate between 2 probabilities. So in other way, or another way to say it, for example, what we are doing here, we have a point x. We are taking now the estimation from the distribution P point of view. And what we are taking basically how likely this point would belong to P and not to Q, or to distribution P and not to the distribution Q. So it is also defined as expectation of the logarithmic difference between the probability PQ and PX and QX, where the expectation is taken using the probability PX. So if we look there, it's also, this is what is basically the definition there. So if basically, again, in logarithmic, we can do that. For example, convert the division here into subtract. So it is the logarithmic of px minus logarithmic of qx. And this is kind of a distance measure, like the difference measure between these two probability distributions. With a value of 0, that means they are the same. In this case, for example, sorry, if the value is 1, that means they are the same distribution, basically. So let's look again at the two machines example. We have machine 1 and machine 2. They have different distributions, distribution 1 and distribution 2. If we want to estimate now the KL divergence between these 2 points, we would take, for example, we apply the KL divergence formula. We are taking the probability or the expectation from the point from machine 1 or machine 1 point of view, basically. So these values are taken from here, 0.5, 25 multiplied by 0.25 divided by 0.5 here. So P here is our machine 1 distribution and Q is machine 2 distribution. Then the divergence there is equal to 0.17. If I estimate the divergence, or if I apply the same formula but I put PP here, I would get 0. That means there is no divergence at all between these two distributions. Because here, as I said, if it is the same, this would be 1, then this would be 0. So now if we estimate the divergence between different distributions, I just here basically change machine 1. I made machine 1 is a bit similar to machine 2, but here instead of 0.125 and 0.125, I made it 0.15 and 0.010 here. So it is more similar than the one before, as you see. And if we estimate that, also the divergence will tell us the same, because the divergence here is 0.005. It is not the same, but has a lower divergence than 0.17. So KL divergence is used as a probability distribution similarity measure. And for example, here we see the divergence between these two distributions. And here we see the divergence between, for example, this is our reference, which is the blue one. Then here we see for the red, then here, for example, for the orange or yellow, and then we have the green. And of course, the further the distribution is from the original one, the higher the divergence we get. So, for example, the red one is the closest one to the original one, which has the lowest divergence. So the cross entropy is related to KL divergence. And if we use a different probability distribution Q to for example, when we talk about the cross entropy, or when we talk about the entropy itself, this was the formula of the entropy itself. Now, if we replace Pi there with another distribution, which is Qi, then the entropy, or it's called the cross entropy in this case, could be used also as a similarity measure between two distributions. So, for example, this is our, again, entropy tree or schema, where we have for machine 2. And if we use now the distribution from machine 1 with the schema of machine 2, we'd get end with the higher uncertainty than the original uncertainty we had for machine 2, because the original uncertainty we had for machine 2 is 1.75. When we now used a different distribution, we ended up with a higher uncertainty, which means we diverged now from the original uncertainty there with some values, and now we get 2.25 questions we need to ask if we assume we are using the distribution from machine 1. So of course, the lower the cross entropy, the more similar the two distributions are, which means also the lower the divergence is. Now, what is the relation between cross entropy and KL divergence? They are actually related, of course. The cross entropy, which is here HPQ, is equal to the entropy of Q, which is our target here, distribution, plus the divergence from that target distribution. So as I said, the KL divergence estimate how the divergence of Q from P. So the new entropy, for example, combining these two is equal to the entropy of P plus the divergence. Okay. So cross entropy is used as a loss function in your network. But why, and why we need to compare distributions in your network to do the loss function? Remember we talked about the softmax as one of the activation function, mainly output activation function in your network. Softmax is used mainly for classification, multi-class classification problems. And we said that softmax actually generate distribution of let's say, confidence about certain class. For example, now we have distribution that generated by the softmax, and as I said before, if let's say we have certain input, then if this input belongs to class 1, then the output of neuron 1 would be, let's say, 0.9, which means 90% it belongs to neuron 1, and 10% belongs to neuron 2. Now we need to compare this distribution that we got from the softmax with the ground truth or original distribution that we have from the supervised data. Here we have an example. Let's say we have a data set with only 4 examples, only 4 points here, only 4 samples. And this is my ground truth, which means for input A, or for the first data set, data point, the output should be, this is 0, this is 1, because it belongs to class B. And this is called one-hot encoding, because for my first input, I have a human labeler who said that this input belongs to class B. And for the second input, it belongs to class A, for example, which means this would be on, this should be off. And that means also 100% we are sure that this input should be class A, B, because it's a human labeler here, as I said, and this means that 100% sure that should be class A. Again, this is class B, and this is class A. So let's say now this is my ground truth there, and this would be now my prediction from the neural network, which is the output of the softmax. So this, for example, the output of the softmax with respect to the first input, this is the output of softmax with respect to second input, third, and fourth. So now we need to estimate the loss. So I want to estimate how good my system is, because I need to apply that. Also, because I need to know how good it is, of course, but also I want to use it for the backpropagation, because if my performance is too bad, I need to improve the performance. And we have seen in the backpropagation, one of the component of the chain basically of derivatives is the loss function itself that we need to differentiate with respect to the weights. So for example, here, this is what we are doing now. We get, or we estimate the cross entropy of the first point here, so which is actually equal to the sum of the probability of the ground truth of what is called the log it. So we have here 0 multiplied by the log of 0.1 minus 1 multiplied by the log 0.9. Okay, so we are comparing how basically the distributions are generated from the neural network, how diverged it is from the original distribution. For example, in this case, it's 0.10 we get. In this case, it's closer. We can see 0.99. So it's here the system is more confident and is correct. 0.01, 0.16, and 0.10. And the average cross entropy, which we will use in the backpropagation, is actually equal to 1.4, or actually, because here we have the average, we have 4 points. We are just averaging the cross entropy along all the distributions, which is 0.09. If with this you can try to save, this is totally different from here. We would have a higher cross entropy, and we need, of course, to make it lower, make it smaller. Here, basically, now 7. If you have any question, as I said, feel free to ask anytime in our Google chat. I recommend you to actually look again or look closely and slowly at this session, because it's very important to understand how your network works. And the convolution, as I said, is also very important to understand, because it will be the basic of the convolution network that we'll talk about later.